Welcome back to the topic of noise. Today we will be seeing thermal noise. Thermal noise is generally generated by all the resistances. For example, a resistor, a semiconductor, the resistance of a resonant circuit, the real part of the impedance, cable, etc. Thermal noise experimentally was derived as a mean square noise voltage and was given as under root of 4 RK where K stands for Boltzmann's constant, T stands for absolute temperature, B stands for the bandwidth noise measured in Hertz, R for resistance in ohms. This mathematical formula was derived by Johnson based on his experimental results and the theoretical studies by Nyquist, due to which this noise is also called as the Johnson noise. So thermal noise is also known as the Johnson noise. Once we know the mean square voltage of thermal noise, we can also calculate the thermal noise power, since power Pn is nothing but Vn square by R. Since it is a mean square voltage, we can write Pn as Vn square by 2R, which comes out to be as KTBn. So we can calculate the thermal noise power, and from the expression we see that the thermal noise power is directly proportional to the bandwidth. K and T are constants. Here we have a very simple example to calculate the thermal noise power from any resistor. The room temperature has been given to us as 290 Kelvin for a bandwidth of 1 megahertz. We need to calculate the corresponding noise voltage given to us the resistance value as 50 ohms. It is a very simple problem wherein all the values have been given to us, but we need to know what is the Boltzmann's constant. We know the formula Pn is equal to KTBn, which comes out to be as 4 into 10 raised to minus 15 watts. Here you have to be very careful with the units, since it has been given to us as 290 Kelvin and 1 megahertz bandwidth. Therefore, we have taken the value over here as 10 raised to 6. Similarly, noise voltage can be calculated as En square is equal to 4 RKTBn. Friends, please read this as En square. It is not En2. So after substitution, we get the noise voltage to be as 0.895 microvolt. Thermal noise is also called as white noise, since it has a uniform spectral density. Now, what do you mean by noise power spectral density or spectral density? Spectral density is a distribution of power over frequency. So noise power spectral density is a noise power measured in 1 Hertz bandwidth. That is watts per Hertz. It is always 1 Hertz bandwidth, even if the frequency varies from 0 Hertz to tens of gigahertz or 10,000s of gigahertz. But we always measure in the bandwidth of 1 Hertz, and if the amount of noise comes out to be the same, we term it as uniform spectral density. Means a uniform spectral density is if we measure the thermal noise in any 1 Hertz bandwidth from 0 Hertz to 10,000 gigahertz, we would measure the same amount of noise. Therefore, we see that thermal noise is also called as white noise. And therefore, you'll see that the uniform noise power spectral density is a straight line parallel to the x-axis, that is frequency, and the amount of power, noise power that you're measuring is remaining constant. So that's why thermal power is also called as white noise. Thermal noise can also be represented as an equivalent voltage generator. Since we know the thermal noise voltage En square is equal to 4RkTBn, it can be connected in series with the resistor, and this becomes your equivalent voltage generator of thermal noise. On the same lines, we can also represent equivalent current source of thermal noise. Here, we take En square, that is a RMS noise current, to be as 4GkTBn instead of 4RkTBn, where G is the conductance, that is equal to 1 by R. So current source in parallel with the conductance will give you an equivalent current source of thermal noise. Thermal noise can be measured when resistors are in series, when resistors are in parallel. We know that if the resistors are in series, then we can find the equivalent resistances R1 plus R2 plus R3 and so on. So the noise voltage of equivalent series resistance is En square is equal to 4R series equivalence kTBn, and hence we can find En, which is under root of En1 square plus En2 square plus En3 square and so on. Similarly, we can find the thermal noise when resistors are in parallel. Instead of resistance, we calculate conductance, and we know that it is represented as G. So G in parallel will be equal to G1 plus G2 plus G3 and so on. And therefore, your equivalent noise comes out to be as equivalent noise voltage comes out to be as 4R parallel kTBn. My dear friends, please remember over here, we first calculate the noise current of equivalent parallel combination, that is En square, which is equal to 4G kTBn. Then it becomes more convenient to work with noise voltage than current, and therefore instead of conductance we take the equivalent parallel resistance. So we write it as 1 upon R parallel is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, and then we use this value in the formula En square is equal to 4R parallel kTBn. That's it for now. Wait for more such videos to come up. In the next lecture, we will be seeing short noise. Thank you.